Okay guys, we're going to have a quick look at a little bit of the equilibrium part of the AS chemistry syllabus. So this is a fairly qualitative approach to it, and that we're not involving any numbers. There's no equilibrium constants to be calculated here. Okay, so the key principle behind equilibrium is this Le Chatelier's principle, okay, named after the scientist who developed it. So if a change is applied to a reaction at equilibrium, the equilibrium will move to oppose that change. And that's essentially what we apply in all circumstances to work out whether an equilibrium will move to the left or to the right. So if we look at an equilibrium, first of all, if we just look at a general sort of reactant 1 plus reactant 2 sits in equilibrium with product 1 and product 2. What does that mean? Well, it's essentially saying that reactant 1 can react with reactant 2 to make products, but also the products can react with each other and turn back into the reactant. So we talk about an equilibrium sitting to the left hand side, which would mean that we have more reactants than products. We talk about it sitting to the right hand side, which would mean we have more products than we have reactants. If it sits in the middle, then we have pretty much the same amount of reactants and products. So this is a dynamic state in that these reactants are always turning into products, and likewise products are constantly turning into reactants. And as chemists or chemical engineers, our overriding desire would be to turn as many reactants into as many products as we can. Okay, and at that point we are maximizing our yield and maximizing our profit. Okay, so when our reaction reaches dynamic equilibrium, okay, the forward reaction, okay, what we call dynamic equilibrium, okay, so at that point the forward reaction is happening at an equal rate to the reverse reaction. So I often ask, well, what does that mean about the concentration of the reactants compared to the concentration of products? And students frequently say they're equal. Well, no, there's nothing to suggest they would be equal in that instance. Okay. There may be more of these than there are of these, so the concentration of that may be greater if the equilibrium lies to the right. Alternatively, it could be more reactants and there could be a greater concentration of reactants. But what it does mean if the forward reaction is going at an equal rate to the reverse reaction at dynamic equilibrium is that the concentration of reactants and products is constant. They're never changing. Okay, so every time a molecule, if you like, of reactant turns to product, likewise a molecule of product turns back to reactant. So the concentration of those remains equal. Okay, and you'd often see a graph given to you, okay, where we are dealing in the y-axis here in concentration, and here we're dealing in time, maybe in seconds, and you'll get this graph of products here. This is reactants. And during the duration of the reaction, you'll see a graph for products. Sorry. Start that again. Okay. And that's as you would sort of perhaps expect. You would imagine that the concentration of reactants during an equation will go down, the concentration of products will go up, and I'll often ask students, well, at what point therefore is this in dynamic equilibrium? And frequently the wrong answer that we will get will be at this point here, okay, as we see the lines intersecting, and that sort of means that students often think that that is where dynamic equilibrium has been reached. But we say that at dynamic equilibrium the concentration of the reactants and the concentration of products is not the same, which they would be here, but we said that they are constant. So really, it's about that point there. Concentration, if this is concentration here, okay, of products is the same, or sorry, is constant as is that of reactants. Now if you're a chemist and you're running this process, what you want to do is move the blue line up and move that line down. Okay, the green line down, which means you will have more product and less reactant. So you've got more product that you can sell and less reactant that you've paid for left over at the end of the reaction. Also, what you would want to do as a chemist is move the red line back in that direction, for the simple reason that that means you get to dynamic equilibrium quicker, and that really is rate, and moving these lines up and down is altering position of equilibrium. So that's what we're going to look at today, is how do we get the blue line up and the green line down. In other words, how do we shift equilibrium from this side to this side. So we'll have a look at how we do that now. So the first thing we're going to look at, and if you just remember, maybe it's a good idea to have written down that Le Chatelier's principle, where the equilibrium will, if a change is applied to an equilibrium will try and oppose that change. So we'll take just our the one that we had, reactant 1 plus reactant 2 goes to product 1 plus product 2. So let's say the examiner said to you, alright, so you're going to add more, so you're going to add some reactant 1 to it. So how does the equilibrium shift to oppose that change? Well, if you add R1 to it, the equilibrium will want to remove it, so it will want to oppose that change. So the only way that the equilibrium can remove R1 is by combining it with R2 and turning it into product. So that would move your equilibrium from the left to the right. Alternatively, if I was to remove R2, okay, how would my equilibrium change then? Well, if I remove R2, the equilibrium will try to replace it. Okay, how does it replace it? Well, the only way it can replace it is by product 1 and product 2 turning back into R2, sorry, and that would therefore move the equilibrium to the left hand side. Common trick of engineers is to remove product as soon as it's made. Why would they do that? Well, let's say we remove the product, either 1 or 2, it doesn't matter. What will the equilibrium do? Well, again, the equilibrium will try and oppose the change. So it will try and make more product. How does it do that? R1 plus R2 makes product. So that would shift my equilibrium to the right hand side. So that's what will happen if I add or remove product or reactant, or increase or decrease the concentration of product or reactant. My equilibrium will move to the right or the left. Okay, so that's sort of adding or removing product or reactant, or changing the concentration. Let's look then at another change that we can carry out. Let's say this time we will increase the temperature or decrease the temperature. Now we need to get a bit of information about the equilibrium in this instance, and that piece of information we need is about the energetics of the reaction. So let's say this time the delta H is negative, and hopefully you all know that that means it's exothermic. Okay, so you have to know that bit of information first before you can start deciding on which direction the equilibrium will move based on change in temperature. So if a reaction is exothermic, remember that the delta H refers to the forward reaction, okay, unless it's specifically stated in the question that it refers to the reverse reaction, which would be unusual. But let's say, okay, so what does that mean? Well, that means it gives out heat. So in other words, P1 plus T, P2. Now we don't write heat in because it's not a chemical, but we can sort of put it in there to help us work out what the change will be here. So if I add degrees Celsius to it, if I add heat to it, is what I'm saying, the equilibrium will try and oppose that change. So therefore the equilibrium will remove heat. So P1 plus P2 plus heat gives me reactants. So the way in which we can remove heat is the same as the way in which we removed reactants or products. So we would shift the equilibrium back to the left hand side. Okay? So if you have an exothermic reaction and you increase the temperature, it will move in the reverse way. And the reverse way, as we hopefully know by now, is in the endothermic direction. And it's no big surprise that if you increase heat, a reaction would move in the endothermic direction. If then I have an exothermic reaction as a forward reaction, and I remove the heat, so I'm taking this away this time, well, the equilibrium will try to replace that. And how does it do that? Well, if it reacts the two reactants together, it makes P1, P2 and heat, so it has replaced the heat, so that would cause it to move to the right hand side. Again, Le Chatelier's principle. It will try and oppose the change which you have made. So that's how you work out how equilibrium changes with change in increase or decrease in temperature. First thing you need to know is the delta H positive endothermic or negative exothermic, and then an increase in temperature drives it in the endothermic reaction, okay, so in the endothermic direction, and a decrease in temperature drives it in the exothermic direction. So as long as you know which direction is which, based on the thermodynamic data that or information that you get in the question, you should be able to work that out. Let's look then at how pressure will change. We've looked at concentration, okay, in the first one, which is really just adding or removing reactants or products. So let's look this time at pressure, and the first thing we look, if we're going to give an answer to say that an equilibrium would be affected by pressure, would be, are the substances in that equilibrium gases? Because if they're not gases, you cannot affect the position of the equilibrium by pressure. So here we go. We have all gases, so this is what we call a homogeneous equilibrium, where everything is in the same physical state. And again, that's a term you have to know. Heterogeneous equilibrium would be where you have solids and gases, or solids and liquids and things are in different physical states. So the key here is that if I increase the pressure, the equilibrium moves to the side of least moles of gas. So in the last one, the first thing we had to ascertain was whether the forward reaction was exo or endothermic, to decide on whether an increase or decrease in temperature would affect the equilibrium and in which direction it would move. This time with gases, we're counting the number of moles on the left and the right hand side. So here I have my imaginary 1 plus 3, so I have 4 moles on that side going to 2 moles of gas on that side. So in this equilibrium, if I increase, let's say the question is, what would happen if you decrease the pressure? Well, if I increase it, it moves to the side of least moles. So logic tells us that if I decrease the pressure, it'll move to the side of most moles. So in this case, it would move from 2 to 4. So it'll move from 2 to the side with 4 moles of gas. So it moves from the right hand side to the left hand side. If there was the same moles on each side, it wouldn't make any difference in terms of pressure. Likewise, in the previous one about heat, if the energy change or the delta H was 0, temperature would leave the reaction unaffected. Okay, if I increase the pressure, of course the opposite will happen. Increase the pressure, it'll move to the side with least moles, so it'll move therefore from 4 moles to 2 moles of gas, and therefore of course it would move from the left hand side 4 moles to the right hand side, which would be your fewer moles. So that's really how you work it out. When you're asked to answer a question like this, guys, don't just say move to the side of least moles or the side of more moles. Quote the number of moles on each side of the equation. Okay, that's frequently in a mark scheme. Okay, so that's concentration or adding or removing reactant. That's pressure done. That's adding or reducing or removing heat, or increasing or decreasing the temperature. Okay, the last thing we'll look at then is if I was to add a catalyst to the reaction. Okay, so if we look at just at an energy profile. Okay, so here we have enthalpy. Okay, and here we have time. This is our time in, let's say, seconds, right? So let's say I have a reaction where I have reactants, I have products, and this then is my activation energy. So that's the energy I need to get from reactants to products. Now, so I'm going reactants to products, just as I had in my previous equations. If I put a catalyst in, a catalyst reduces the activation energy. So my new activation energy with a catalyst is the red arrow, so it's smaller than the previous activation energy. Now, a catalyst has no effect on the position of equilibrium, because a catalyst does reduce the forward activation energy, but it reduces the reverse activation energy by exactly the same amount. So yes, you will go from there to there at less energy, but you'll also go from products back to reactants at less energy. So the rate of the forward and the reverse reaction are lowered to the same extent, or sorry, sped up to the same extent. Okay, so therefore there is no effect of a catalyst on the position of equilibrium. It does affect rate, so it does affect how quickly we get to dynamic equilibrium, but it does not affect the actual position. Okay, I hope that explains equilibrium a little bit for you, and that it'll have cleared a few things up for some of you. If you need any extra help, please come see me.